All right, guys. So this summarizes most of the reactions in organic chemistry. What we have to make sure we do is that we understand what a molecule is representing or acting as. Because every molecule can act as a base or a nucleophile, especially if something that's charged, okay? Negatively charged. It can act as a base or a nucleophile. So something that's negatively charged can be classified as a base or a nucleophile. It could either be a good base or a good nucleophile, and we'll discern that in this column right here. So NaOR, we never write it as RO minus in the exam. They give it to you as NaOR. We know in chemistry that when it hits solution, that Na is going to leave. So NaOR is really just O minus R. And what is R? R is any carbon chain. So if I see one carbon chain attached to an O minus, that's not going to be hindered, because this category says strong base unhindered good nucleophile. We will get to what hindered looks like, but this is the first category. So our O minuses, which usually are presented as, KOR or NaOR. That's why I even wrote this as KOH, because OH minus is definitely not hindered. It has an H attached to the O minus. So it's definitely not hindered at all. So these are not only good at being bases, they're also good nucleophiles. So they're strong bases and good nucleophiles. Again, if there is just one R group coming off an O minus, it's not going to be hindered, okay? It is not hindered if there's one R group attached to the O minus. And OH minus is definitely not hindered as well. Let's talk about the next section right here. Strong bulky base that's hindered, poor nucleophile. Bulkiness matters with nucleophilicity, okay? That's where basicity and nucleophilicity don't parallel each other, is bulkiness. Because something to be a good base, or I'll use the term strong base, but a poor nucleophile. Because in acid bases, we learn that CH3 groups, right? Alkyl groups or R groups are electron donating groups, okay? Well, electron donating groups, the same ones that we learned in acids and bases, because we talked about bases, push electron density and make that negative charge stronger and more focused to grab a proton, okay? Now, usually I want to write this as an R3, by the way, but I'm giving it to you like they give it to an exam. You have like an R3CONA. That's the same. I don't know why I wrote, no, I know I wrote that because the C is connected to the O, pardon me, but they never give it to you as CO minus by itself. They put an Na or a K or a metal beside it. So on your exam, whenever you see a metal, scratch it out. It's really a full negative charge, okay? And then R2 NNA was kind of confusing, but that's really just N minus because you scratch out the Na. What's the difference between R2 and H2? R2 means that you have two, or in this case, three R groups or CH groups coming off of the alpha carbon, okay? The alpha is the first carbon, by the way, if I use that fancy terminology. Like I said, one group coming off is not hindered. 3 or 2 is when we start talking about the conversation of hinderedness. Like I was saying, the carbon that's attached to the negatively charged atom, like oxygen or whatever we're dealing with, nitrogen, that first carbon coming off is called the alpha carbon. Hinderedness only matters in the alpha and beta positions. So the first carbon and the one after. However, what I want to really nail home is that if you see just one R group coming off an O minus, that is not hindered. 3, yes. 2, yes. 1, no. So these, again, are strong, bulky bases or hindered bases, hindered nucleophiles as well. They're not good at being nucleophiles because in SM2, that's a conserved reaction. Okay? It does a backside attack, does inversion. Okay? You don't want your nucleophile to be bulky or hindered. You don't want it to be that. That's what makes this a poor nucleophile, but a good base. What makes a good base is electron donor groups, or there's more R groups. It says 3 R groups right here. These are not only good at being a base, but good at being a nucleophile. They have options. These are good at being what? A base. Poor nucleophile. So if you see something with a bunch of CH3s coming off of the alpha position, which is that first carbon that's attached to the electronegative atom, you're gonna be thinking, what could happen? It's bulky and it's a poor nucleophile, so I probably won't be doing substitution nucleophilic, because that's what SN2 stands for, substitution nucleophilic, right? Then we get to this section. These are the weak bases, good nucleophiles. Now, we learned what makes a base weak. Well, a base is weak if it's stabilizing the negative charge and it's unreactive and it's happy where it is. A strong base is unstable and reactive. Okay? Like this R3, those electron donor groups make that O- more reactive, more unstable, and stronger. I- is the conjugate base of the mineral acid HI, and it's large in size. It's able to stabilize that negative charge, so it's not a very strong base. So I'll make sure I'm still recording. Oh, I sure am. So that being said, I'm giving it to you as if they give it to you in an exam. If there's RS and A, because they're not going to give you RS minus. Okay, they're going to give you RS and A, or give you some metal attached to it. But we just know as studying that you just scratch with the Na and it's a full negative charge on the S. HS and A. Cool. Scratch with the Na. There's a negative charge on the S. Ki. Cool. Scratch with the K. That's the same as I minus. Hi is not the same though. If it was Hi, that'd be an acid. Okay? Hi doesn't just break apart fully in solution. Okay? It has to be deprotonated and all that, right? Whereas these, with a metal and ion, when they hit solution, they just dissociate. So if you have like HBr or Hi, usually those are reactions or questions where you have like an OH, poor leaving group, grabs a H off HBr, Hi, forms oxonium, kind of like this. Water, but there's an extra bond, right? There's a positive charge. Whatever, we'll get to that after. So, NABr, cool, same as Br minus. NaCN, Cn minus, okay? NaN3, N3 minus, okay? So these are weak bases, but good nucleophiles. So anything can be classified as a base or nucleophile. This category is weak base or nucleophile. Here, in the last part of our column here, we have weak base or nucleophile. This was weak base, good nucleophile. Okay, this is weak base, poor nucleophile. So, as expected, what we have is things that are neutral, like alcohol and water. They're weak bases, and they're poor nucleophiles. So what did we just cover? Why is it important to know this? Why is it important to see that if I gave you NaOCH3, and if you should write that on your paper, NaOCH3, that's not hindered. That has one R group on it. That's this section. NaO C, big brackets, CH3, but 3 CH3s coming off of it, that's hindered. But just one CH3, or here's another one, NaOCH2CH3, also known as ethoxide, has one R group coming off it. That's not hindered. You have to be able to recognize these to succeed. Now, I don't know, KOH has an H, it's an O minus, that's a strong base, good nucleophile. If you have CH2, CH3, but 2 of them coming off an N, and there's an Na beside it, that's a strong, bulky base, poor nucleophile. If you have here Ki, weak base, good nucleophile. Any of the halogens fit in this weak base, good nucleophile. Sulfurs, neutral or negatively charged, weak base, good nucleophile. Water and alcohols, poor base, weak base, poor nucleophile. You can say weak or poor, it doesn't matter, it's just bad, okay? Like if you're water or an alcohol, you're a weak base and a poor nucleophile. That's it. So you have to make sure you know these. That if I see water, I can't think SN2. Do I see SN2? But I'll go through each scenario with you, but you have to know that water in an alcohol is a weak base or a poor nucleophile. Okay? Or if you have RO minus, that's a strong base and a good nucleophile. Okay? And then that is a strong bulky base, poor nucleophile. Okay. So now I just focus on the major reactions. I don't care about the minors. I just want to focus on what's going to happen. Okay? So if you have a strong base that's unhindered and a good nucleophile, just want to make sure I'm still recording. If you're methyl, you're going to do an SN2. What does methyl look like? It has a C and 3 H's coming off of it, right? And what is up here? These are just the types of alkyl halides. Because usually, your leaving group, a good leaving group is an alkyl halide. Okay? So, excuse me, but, and all this is showing in the columns is how your alkyl halide or how your substrate or electrophile is changing. What if I attack a methyl? What if I attack a primary? In FYI, primary just means there's one carbon attached to it. Secondary means there's 2 carbons attached to it. Attached to what? The alpha carbon that's attached to the leaving group. Okay? And then tertiary, 3 carbons attached to it. So, if you have a strong base that's unhindered and a good nucleophile, you have a methyl, that's SN2. It's going to do backside attack, inversion. It's not hindered, electrophile. Now, just so we don't get confused, I'm going to use the word bulky from now on to explain this part of the chart. I'm going to use the word bulky when I talk about what's attacking, and hindered when I'm talking about the substrate of the electrophile. Okay? So I'm going to call this unbulky. I'm going to call this bulky. Okay? Then I'm going to call hindered, because this is what we call hindered. This is very unhindered. Okay? So I'm going to use, just so you know what I'm talking about. So methyl is very unhindered. Okay? Has 3 H's coming off of it. R groups are what block the way. And because my base or nucleophile is not bulky, okay, I can easily go into a backside attack. You can't form, by the way, a double bond with 1 carbon. Last time I checked. That's why there's not going to be an E2 reaction. And let me just give you guys a crash course on what SN2E2 is. SN2 is the conserved reaction. It's 1-step, inversion, backside attack. It's substitution, nucleophilic 2 is 1-step. E2 is elimination. Elimination reactions, whether it's E2, there's no E1 on this chart. There's no E1 on this chart. There's a specific scenario for E1 that we'll get to, but E2 forms double bonds. Okay. If you form double bonds, if you don't know what's going on in the exam and you see that a double bond's formed, elimination most likely happened. Okay, SN1, leaving group leaves, 2 steps. That's all that happens. Okay, so back to here, now we're at primary. What does it say? These act as strong bases and good nucleophiles. So if you have a primary, it's not very hindered. This is not very bulky. We're still going to do SN2. Okay? Now we're getting to secondary. My substrate, my electrophile, my alkyl halide is getting more hindered. And last time I checked, my molecule, like NaOR, RO minus, or OH minus, is not bulky. And it's good at being a base and a nucleophile. So when I see secondary on my exam, I'm gonna be like, E2, E2, when I see secondary. When I'm good with a strong, unbulky base, good nucleophile. Do you see why it's important to recognize this in order to determine this? You need to know what this is classified as to get to this. You need to know the molecule is a strong base and a strong, unbulky base and a good nucleophile to determine what reaction happens. In tertiary, SN2 never happens in tertiary. You can check out my previous videos. The substrate's too hindered. SN2 also does not happen for aryl or vinyl. SN1 also doesn't happen for aryl or vinyl. Go back to the previous video. So, strong, bulky base, poor nucleophile. Methyl still forms SN2 happens. Why? Doesn't it say it's a poor nucleophile? But can you form a double bond with 1 carbon? No, you can't. That's why SN2 happens. In fact, in methyl, SN2 always happens, except for the weak base poor nucleophiles. There's no reaction. Okay? So again, strong, bulky base, poor nucleophile, methyl, it's still SN2. Well, right at primary, goes E2, we form a double bond. Why is that? Well, it says it's a strong, bulky base, but a poor nucleophile. In substitution reactions, we act as nucleophiles. In elimination reactions, we act as bases. That's why you have to know if it's good at being a base or good at being a nucleophile. Based on the definition of this category that we learned, it's strong at being a base and it's poor at being a nucleophile. So if it has the choice, what's going to do? It's going to act as a base and it's going to perform elimination. Okay, and if you forget, SN2, it has the letter N in it, or SN1, it has the letter N in it. So in substitution, your reagent acts as a nucleophile, because nucleophile starts with N. In elimination, your reagent acts as a base. And in elimination reactions, we make double bonds. Whew. All right. For secondary, what happens is that if you have a strong, bulky base, poor nucleophile, it's just going to do E2 again. Secondary is more hindered than primary, which is more hindered than methyl. The more hindered you get, the less chance you're going to do an SN2. Plus the fact that I said it was strong at being a base, and it's a poor nucleophile. Because it's going to be a base, it's just going to keep doing elimination. Done. Tertiary, do you see SN2 ever? Even for the unhindered nucleophile, there's no SN2 here. Because tertiary doesn't happen for SN2. So doesn't aryl, so doesn't vinyl. Tertiary never happens for SN2. Okay. So tertiary, and this is half the battle, because E2 branches off into two categories. Okay. E2 branches off into Hofmann and Zaitsev. Strong unhindered bases will form the Zaitsev product, or the most substituted double bond. What do I mean by substitute? When you have a double bond, how many groups are coming off of it? That's how substituted it is. It has like 4 carbon groups, is what we call tetrasubstituted. There's 3 trisubstituted. 2 is di. So that's fine and dandy. But what I want to say here is for E2, if it's unhindered, we form Zaitsev. If it's bulky, we form Hofmann, the less substituted double bond. Okay? And that's when your reagent is acting as a base. Getting E2 is half the battle. From then, you have to decide if it's going to be Hofmann, which is this category, or if it's Zaitsev, which is this category. Okay? So now we're looking at the weak base good nucleophiles. Let's review. In substitution, your reagent acts as a nucleophile. Yes, it has the letter N in it, SN2, SN1. In elimination, it acts as a base. Weak base, good nucleophile. It's bad at being a base because it says weak, right? And it's good at being a nucleophile. Substitution reactions, my reagent acts as a nucleophile. So just by intuition, no matter what alkyl halide they throw at me, I should expect substitution to dominate, right? And like this one, because it was a strong base poor nucleophile, no matter what reagent they give me, I would expect elimination to dominate, right? Because in elimination, your reaction is acting as a base, right? So, okay, well, again, on the exam, they don't give it to you as S-, they give it to you as R, which would be like CH3, SNA, or KI, NABR. Again, when you hit solution, you scratch it off, it's Br- or I-, right? Halogens. What happens is, well, we talked about this, as you get lower in the column, or the bigger the size, for nucleophilicity, it's more polarizable. So it's more nucleophilic. So between fluorine, chlorine, bromine, iodide, what happens is that the iodide ion is more polarizable. It's most nucleophilic. Okay, so it's bad at being a base. It's good at being a nucleophile. I don't really care about hinderedness. Like these two, I care about hinderedness because the hinderedness not only tells me what reaction happens, it also tells me if it does E2, if it is Hofmann or Zaitsev. So not only do I have to know what, I'm going to use the word bulky, sorry, I should be consistent. Bulkiness of the reagent not only tells me if SN2 or E2 happens, it also tells me deeper into E2 if Zaitsev forms or Hofmann forms. Okay? So, weak base, good nucleophile. Methyl, SN2. Have we seen any elimination in methyl? No, because you can't form a double bond with one carbon. You just can't. Have I seen any SN2 in tertiary? No, I haven't seen the SN2 in tertiary because it's too hindered. It also doesn't happen in aryl or vinyl, by the way. Weak base, good nucleophile. Methyl is SN2. Primary, also SN2. Secondary, SN2. I'm just changing. I'm just making the reagent more hindered. Tertiary, SN1. SN2 anymore. It's too hindered. I don't do SN2. I do SN1. Where my leading group leaves, I form a carbocation, and then my reagent can attack top or bottom. So, does it make sense that substitution dominates in this? Are you guys listening to me? Like, it makes sense, doesn't it? Because it's good at being a nucleophile. That's why. And then over here, let's look at, well, before I jump here, let's look at here. It's strong at being a base. And elimination, your reagent acts as a base. That's why I see a lot of E's, don't I? I see a lot of eliminations. Now over here, we have weak base poor nucleophile. These really can't do anything. They don't have a negative charge. These have negative charges, that's why I can put an Na beside it. Okay, that's an ionic bond. It's kind of like when you're grade 5, NaCl, you know, it's really Na plus and Cl minus when it hits solution. These are neutral. So, these are weak bases. If they ask you an acid-base question, anything like water and alcohol is a really weak base. It's not negatively charged. You're electrophile. When you do substitution reactions, it's positively charged, and if your reagent's not as neutral, it's not very reactive. So these are weak bases. Point of see alcohol. Do not mix up ETOH, okay, and ETONA. ETONA is a strong, unbulky base, good nucleophile. ETOH is an alcohol. That is a weak base poor nucleophile. H2O is a weak base poor nucleophile. OHONA or NaOH is a strong and bulky base good nucleophile. One has a full negative charge. These are neutral. They don't do a lot. They're not very reactive. So I go to methyl and I don't even have a reaction because they're not good nucleophiles. Do I do elimination with methyls? No, I don't. I don't because I can't form a double bond with one carbon. I just can't. Do I do SN2? Have I seen SN2 in tertiary? I've never seen SN2 in tertiary. It also doesn't happen for air or vinyl. It doesn't. So if you see a halogen right on a double bond, nothing happens with SN1 or SN2. I said that 3 times. So we got primary, right? No reaction still. Why can't you form an SN1? You don't form carbocations on methyls or primaries, okay? The carbocation is electron deficient carbon. And it's stabilized by hyperconjugation, or when electron donating groups or electron density is given by like R groups, like carbons and nitrogens. Primary only has one R group. Okay, we also talked about that, how one R group's not bulky, by the way, that's an FYI, but if I have one R group, positive charge, it's not stable. I don't even have SN1 happening in these, because these are usually your SN1 go-tos. You see this, listen, you see water, you see alcohol, SN1, 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 okay? So don't tell me that that's gonna do SN. Do I see SN2 here? Oh, it's a weak base, it's gonna do E2. It's not gonna do E2. Are you kidding me? Like, it's SN1, but methyl primary doesn't have SN1. It doesn't. Because I'm not gonna form a carbocation on a methyl. That's a C plus by itself and 2 H's. What are the H's gonna do? Hey, give me some like electron density. Nothing's gonna happen. The H can't donate electron density. Can't help out the poor in electron density carbon. Also primary, there's no SN1, there's no reaction. Okay? So if you ever see an alcohol or a water, there is no SN2, there is no E2. You need something that's decently good as a base or decently good as a nucleophile. In fact, these are strong bases, unbulky, good nucleophiles, strong bulky base, poor nucleophile. You need to be good at something to do an SN2 or an E2, or else you do SN1. Okay. E1 happens in this course when you have H2SO4 concentrated and heat. Doesn't matter if the heat's under the arrow, no. Just think about concentrated H2SO4. If they put H2O underneath, if they say dilute H2SO4, that means there's water. Water is weak base, poor nucleophile. So after that happens, you form a carbocation, right? Okay, after you form a carbocation, it's going to do an SN1 type of reaction if you see dilute. If not, you just form E1. Okay. So secondary and tertiary, your substrate's more hindered, your alkyl halide's more hindered. And hey, now I can form a carbocation on a secondary or a tertiary. Okay? Because hyperconjugation, what does that mean again? Carbons and hydrogens have electrons. So if there's a positive deficiency, if there's carbon hydrogens around it, they're going to inherently donate electron density to stabilize that positive charge. SN1 does not happen, E1 does not happen, which we really didn't talk about that much, but E1 forms a carbocation, by the way, as well. Does not happen on methyls, primaries. E1 definitely doesn't happen on methyls because you can't form a double bond with one carbon. In primary, you're not going to form a carbocation on primary right there, one carbon. Secondary, tertiary, what we do is SN1. You gotta wait for the leaving group to leave, you form a carbocation, there may be a shift. Remember, every single time you form a carbocation, there'd be a methyl shift or a hydride shift. And you have to look at the beta positions. Beta is one away from the alpha. The alpha is where the carbocation is, the carbon attached to the leaving group. No, that's alpha. Okay. Just focus on that, I would say. So again, weak base poor nucleophiles. Never SN2, never E2, SN1. Every single time we form a carbocation in that SN1, you look at the beta positions. You also look for beta positions as well when you do E2. Because you have different types of beta hydrogens, okay? Certain beta hydrogens, if you take them off, they're going to form a more substitute double bond. That's what we call the Zaitsev product. That happens when it's a strong, unbulky base, good nucleophile. If it's strong, bulky base, poor nucleophile, then you're from the Hoffman product. You look at the beta hydrogen, that makes less substituted double bond. If you're bulky, you don't care to go the extra mile and make the most substitute double bond, you just want the reaction to be over. So what are beta hydrogens? You look at the leaving group, okay? The carbon with the leaving group attached to it, your alkyl halide, okay? And then look left and right, whatever's one single bond away from that one, any hydrogens attached to those carbons are beta hydrogens, all right? Don't forget as well, it has to be anti. So if you have a ring and stuff, it has to be anti. If your H is wedge in the ring, if your leaving group is wedge, your H for the E2 has to be dashed. Those have to be anti-coplanar to each other. That's enough for this video. Watch it a couple of times, ingrain this in your mind. Thanks for watching.